I'll speak into this, that's fine. All right, thanks very much for the introduction, Robert. So yes, I'm Derek Murray, and I'm going to be telling you about Naiad, which is a system that we've built at Microsoft Research. So Naiad is a new system for large-scale distributed computation. And this is a very, this is a very crowded field. In this session, you're going to hear about, or you have heard about, 4 systems that inhabit different points in this space. So what is it that makes Naiad different? The problem, as we see it, is that every time a new distributed programming model is introduced, it's tightly coupled with the underlying execution model. And this has led to a proliferation in vertically integrated systems that struggle to interoperate with each other. Now, what do I mean by this? For example, we have batch processing frameworks like MapReduce, Naiad, and Spark, which you just heard about. And these are based on the stateless, deterministic, and synchronous task execution model. We have stream processing systems like Storm, Seep, Millwheel, TimeStream, and the like that use an asynchronous streaming model. And we have graph processing systems like Pragle, and GraphLab, and Giraffe that are specialized to use a vertex-oriented execution model. So if you want to write a program that combines one or more of these models, well, 2 or more, you end up having to use the lowest common denominator. And for some workloads, this is just fine. And the lowest common denominator here is batch processing, I forgot to say. So for some workloads, this is just fine. We heard in the last talk how a batch system, Spark, can deliver sub-second latency for many streaming workloads. But what if, say, you wanted to feed your stream into a graph processing algorithm, or combine the results of a graph-based machine learning algorithm with the results of a batch job? We've seen over the years that batch systems are inadequate for this task, and this is why so many specialized systems have bloomed in this community and other. So with timely data flow, what we've aimed to do is raise the common denominator, supporting all of these different workloads and their combinations, and we use this model to build a system, Naiad, that achieves the performance of specialized systems while still giving the flexibility and the expressiveness of a generic framework. To give you an example of the sort of problem we're trying to solve, let's start with an iterative graph algorithm. So let's say we want to find the connected components of a graph. You can do this efficiently in an iterative manner with Pragle or GraphLab. To make things more interesting, let's derive this graph from a corpus of Twitter messages, extracting username mentions from the text and using these to create edges in the graph to give us the mention graph. Now, doing this for a static graph is all well and good. We have to combine some ETL and some graph processing. That's not so bad. But tweets are posted in real time, so we might want to update this graph in real time, feeding it into the graph computation, updating the graph, and maintaining the connected components in, say, a sliding window. This is already getting into uncharted territory, but we can go further. Let's take those tweets and feed them into another computation. We'll take the hashtags, extract them, and join that computation with the result of the connected components. We can then aggregate those data to find the most popular hashtags in a component and track that in the same sliding window. We'll go even further. Let's add another streaming input. This one's going to be for interactive queries. So a query comes along, it's a username. We're going to join it with the set of components and then join it with the computed aggregate, the maximum most popular hashtags, to find the most popular hashtag for that user's component. And you could imagine how you might use this to build a web page containing topics or adverts that are related to a user's social community. So how might we build a system like this? The arrows suggest that we're going to have some kind of data flow, and that's good because we know how to parallelize that. We know how to distribute it. But the key idea is that we have to minimize the latency of the coordination in this system so that the system is able to perform fine-grained work like processing an incoming batch of data in less than a second, responding to the queries in less than 100 milliseconds, and at the core, iterating the connected components algorithm in less than a millisecond. And this talk is going to focus on how we achieve these latencies in Naiad. But first, I want to revisit data flow and why that's an appropriate starting point for our work. So you've seen plenty of slides introducing data flow at this conference. I won't labor the point. Let's just introduce the terms. We're going to have a directed graph of stages, which represent computation, and connectors that represent the paths along which data can flow between the stages. And the reason data flow is so popular, in one form or another, it's the basis of MapReduce, Naiad, Spark, Dandelion, several other systems, is because it's easy to parallelize. Each stage can have a data parallel implementation in terms of physical vertices that work on independent chunks of data. And these are just sequential pieces of code that can be running on any machine in the cluster. The connectors are what take care of moving the data around. So these can be simple pipelines with an edge between and a one-to-one mapping between vertices. Or they can be data exchanges, like the reduced step of a MapReduce job, where the system takes care of routing the data based on some key in the data. If we add cycles to the Dataflow graph, this lets us run iterative algorithms. So vertices in the cycle can execute a data-dependent number of times. And that means the Dataflow can compute things like graph algorithms where the number of steps to fixed point is not known ahead of time. So we could use a batch execution model to execute this Dataflow. But to understand why it's not always sufficient, it's instructive to consider how these Dataflows execute in two different models. So looking at a single vertex, a batch system like Naiad or Spark has synchronous, deterministic, and stateless execution. So all of the inputs for the vertex must be available on hand before the stage becomes active, and then it runs for a while, produces some outputs, and throws away its state. By contrast, a streaming system like Storm runs asynchronously. A vertex is always active, and when input comes in from any source, the vertex can produce output immediately. So these two models have strengths and weaknesses. Asynchronous streaming is typically more efficient in a distributed system because independent vertices can run without coordination. But sometimes you need synchronous execution. And I think some of the questioners at the end of the last talk raised this point. If the vertex has to compute an aggregate value like a count or an average and associate it with some prefix of the input, this requires the system to perform some coordination to know that all of the messages or records have been received. So returning to our cyclic graph, we see that if we're executing in synchronous batch mode, the batch of data arrives at the input, then will move through the vertices in lockstep, finally reaching the output and sending a batch of result. And the nice thing about this is there is a one-to-one correspondence between the input and the output, but the cost is in the latency because there's no overlapping of computation within the graph. In a streaming setting, all of the vertices are active all of the time and they're able to maintain mutable state. So the data stream in. This leads to data flowing around the loop, and eventually data will be produced. The latency can be much lower, but the correspondence between input and output is lost, making it hard to do things like keep a sliding window of the counts, of page views, like we saw in the previous talk. The aim of timely data flow is to reconcile these two models. So whenever it's possible, the vertices can run asynchronously without any coordination. But when it's necessary, vertices can synchronize to produce consistent results and simulate batch execution. The main idea, and the reason for the name, is that every message in the system has a logical timestamp, and this can be used to track progress in the system, as I'll show in the rest of the talk. So I'll spend the bulk of the talk talking about how we achieve low latency, and start off with the timely data flow programming model. This programming model is event-based, so all execution for a vertex happens in the context of a callback, which I've shown in the dashed box, and vertices interact with the outside world by performing operations. We have two callbacks and two operations, and that's the whole programming model. So the asynchronous primitives are for message exchange. And indeed, all message exchange in a timely data flow graph is asynchronous. When a vertex B is running, it can invoke the sendBy operation, specifying one of its outgoing edges, the body of a message, and a time. Now, this time identifies records that are associated with the same batch of data. You could think of it as a sequence number that's applied to the data, but we'll extend that to something more general later on. However, since the message delivery is asynchronous, the system is free to deliver the message without having to reorder it at the receiver. And so it does this by delivering an on-receive callback to vertex C here, by passing the same edge, message, and time. Sometimes, though, you need synchronization, and for that reason, we have notifications. And these are delivered in a specific order so that we can simulate batch execution. So when vertex D is active, it can request a notification by calling the notify@, operation, specifying the time at which it wants to be notified. And this is time in the same sense as we applied to the message exchange before. This doesn't block execution, so D can continue to receive messages and do some processing and on-receive. So it can do things like run combiners or otherwise compress the state. It finally receives the notification in its on-notify callback when all of the upstream work at that time has completed. And once this notification is received, D can tell that it has seen all of the data for that time, allowing it to perform work that requires it to know all of these values. For example, producing the true result of an aggregate, or performing some cleanup once it knows that an operation has completed. While these primitives are quite expressive, they're not the most user-friendly way to write a program. So we've built a number of data parallel frameworks on top. And out of these, I want to call out our incremental version of LINQ as the kind of prototypical example of how you would write a program against one of the APIs. So here we see a stream defined in terms of relational style or functional LINQ operators. And you might remember LINQ from Chris's talk on Dandelion the other day. It's also similar to the Spark streaming RDD syntax. Given a stream of tweets as strings, we're going to tokenize them using the select many operator, filter them down to just the hashtags using the where operator, and perform a count using the count operator. This is basically an incremental MapReduce word count, and it's part of the incremental analysis task, interactive analysis task that I showed you earlier on. And we have a number of these frameworks, and for more details about them, you should read the paper. But one appealing feature of Naiad is that while we have these high-level frameworks, you're not restricted to a single programming model. You can choose to use one of these frameworks, you can combine many of them in the same program, or you can even use none at all, writing your code directly against the low-level API. And this is useful if you know a specialized algorithm that can execute your problem more quickly. We see, for example, plenty of new ways to do graph processing, and that can be you can fit that in to the timely Dataflow model by implementing it directly in the Vertex code. I'll show you a case when we did that later on. So timely Dataflow helps us to achieve low latency by letting you write programs that can combine asynchronous and fine-grained synchronous execution. Next up is the distributed progress tracking protocol, which is how we actually run timely Dataflow programs and make sure they give correct results. So what's progress tracking all about? Well, remember just a couple of minutes ago I told you about notifications. Progress tracking is what ensures that these notifications get delivered at the correct time and in a prompt manner. So to make this work at all, we're going to need a few ground rules. First of all, we'll need the external source of data to give us some information about progress. And what this amounts to is it will assign integer epochs to the incoming data, and at some point declare that epoch t is complete. The next constraint is that vertices may not send messages back in time. And what does this mean? Well, if C is running a callback at time t, this means that all of its calls to send by must be at a time t prime, where t prime is greater than or equal to t. This is the same constraint that Jefferson had in his virtual time system many decades ago. So given just these constraints, we could use existing techniques like virtual time, or like punctuations in stream processing systems to fire these notifications. But a problem arises when we come to deal with loops. So we could have a vertex C that requests a notification, but logically, given the constraints I explained, this notification can never fire. When that callback would run, C would be able to send messages at time t that would have to be delivered before the callback ran. And that's a contradiction. C depends on its own output, and we have a cyclic dependency that we need to resolve. To do that, we add another constraint to the graph. And this is that every back edge in the loop must have a feedback vertex. And this advances the time. It strictly increases the time on every message that passes through it. This makes it possible to have notifications in a loop, but it creates another problem. So since if times are simple integers, as I've said so far, they can be incremented a data-dependent number of times going around the loop. And so if we get some data arriving from A at time 1, when should E request a notification in order to be sure that it has seen all the data corresponding to that input? To resolve this problem, we add structure to the times. The messages inside a loop receive a timestamp that has a second component. This corresponds to an iteration counter. So very simply, it's initialized to 0 when messages enter the loop. It is stripped off again when messages leave the loop. And as messages circulate in the loop and pass through the feedback vertex, this advances the loop counter. This means that E can simply request a notification for epoch 1, and it will see all the data corresponding to that epoch. So how can we use this to actually do progress tracking? Well, the main idea is that the constraints we've imposed on the graph mean that there is an order on events, on outstanding messages and notifications in the system. Now, the order is defined in more detail in the paper. It's called the could result in order. But I'll give you the gist, which is that if you have an event, let's say a pending notification for D at time 1,5, this could send a message to B, but it would have to go through the feedback vertex to get time 1,6, and then transitively to C at time 1,6, and E at time 1, after we strip off the loop counter. We also see it can reach D again at 1,6, and it can never reach A, which allows us to pipeline the processing of epochs, because this event does not precede notifications for later epochs at A. So by calculating these times, we can work out which notifications the event D precedes, and this gives us our order on events. And once we have this order, the basic algorithm is very simple. We just maintain the set of outstanding events, order them according to the could result in order, which is actually a partial order because we can have some task parallelism in the Dataflow graph, and then compute the frontier or minimal anti-chain of these least elements in the set, the elements that have no predecessor in the could result in order. So any notification in the frontier is thereby safe to deliver. Remember, onNotify is called only after all calls to onReceive at the same time or earlier have been delivered to that vertex. And so if the notification is in the frontier, this means that nothing precedes it, and therefore it's safe for the scheduler to go on and deliver it. At this point, I've told you about an algorithm that relies on updating a potentially large amount of shared state every time the set of outstanding events changes. And if you're following along, this should make you a little bit nervous. But fortunately, commutativity comes to the rescue, as it has many times in this conference. We can build a scalable distributed protocol because the way that we update this set is commutative. Now, the full details of the protocol are beyond the scope of the talk, but I'm just going to give you a high-level overview. To start, each process is going to maintain a local approximation of the outstanding events in the system. And this has to be a conservative approximation, which means that if you take the frontier of the approximation, it never runs ahead of the true global value. And that means that the local process can use this approximation to deliver notifications. Then when events are created in notify at, for example, the creating process adds the event to its local approximation. And the same happens when a process does a send by. And then they broadcast information about these events to the other processes, allowing them to learn about these events and update their approximation. When events are consumed in onReceive, for example, the event is deleted locally, and same for onNotify, and then the same broadcast happens, which removes the events from all of the local approximations. And this protocol, as I've described it, works as long as the communication channel is reliable and FIFO. Our colleague Tom Rodehefer worked on a TLA plus proof that formalized and proved its safety properties, and also enabled us to find a number of optimizations, which are absolutely critical to make this protocol work. I've just told you how to do it correctly, but not in a performant manner, so you'll have to see the paper for how we reduce the overhead of sending these messages. So in the second part of the talk, I showed you how we can use a distributed progress tracking protocol based on structured times that lets processes schedule work independently and deliver notifications promptly. I could spend hours talking about the engineering challenges we had to deal with to get this kind of low latency, but I only have a couple of minutes. I just want to draw your attention to one of the unusual challenges we faced when implementing Naiad, and we called this the micro-straggler problem. Because when one of these things occurs, it delays the delivery of a notification, just like a straggler does in MapReduce, but with a much, much smaller magnitude, on the order of milliseconds. These events are too short to deal with by a reactive strategy. By the time a central master would be able to react to one of these, the microstraggler event would have passed. And this meant that we had to take proactive steps to deal with these, and we have some details of these in the paper that might be useful for other people trying to implement low latency systems on a managed runtime. So to sum up this part of the talk, I've shown you how we achieved low latency in Naiad through work at many different levels. By defining an efficient programming model, developing a scalable distributed protocol, and by engineering the system to make the underlying primitives efficient. Now I can get down to some numbers to see if what I said is true. So to tell you about the evaluation, I have to describe the system architecture first. We have a cluster that has several processes. Each of these host workers that are pinned to physical CPUs, and each worker is responsible for processing a subset of the vertices in the graph. Now, the processes know the locations of every vertex, which means they can push messages directly from the sender to the receiver, and remote messages are multiplexed over point-to-point TCP connections. The workers have each have their own scheduler, which has its local approximation of the progress tracking frontier, and it uses this to make notification decisions. And this is backed up by a process local progress tracker that runs the protocol, well, the optimized version of the protocol I just described earlier. As for fault tolerance, and TD pointed this out, which I'm grateful for, there are limitations to the system. And this is that fault tolerance is kind of a second-class citizen at the moment. It's based on consistent checkpointing, and that means if there's a failure, we have to roll back to a previous version of the state. The reason we haven't done fast parallel recovery as in D streams is that to get the latency we desire, we need to have this asynchronous message delivery, and this means that state is mutated in a fashion that can be non-deterministic, so we don't have that clean deterministic boundary. This is an area where we're working to improve things, however. So, given that architecture, how does it perform in a simple micro benchmark? Well, in this one, what we did was we wrote a simple iterative program that performs a global barrier in each loop on up to 64 machines with 8 workers per process. The overall picture is quite encouraging. So our median latency at 64 machines is 750 microseconds. And the error bars show the 95th percentile latency in each configuration. So at 64 machines, it's 2.2 milliseconds iteration latency. 2 things to note here. First is that this is orders of magnitude faster than existing batch systems. So it makes it practical, even with these micro-stragglers sometimes occurring, to run iterative algorithms with very sparse amounts of work. And the other thing is that we're running this on a fairly standard operating system using standard network protocols, which is to say that we have some ideas for how to improve this further. So I'll talk briefly about 2 of the applications we built. The first one is a variety of PageRank. And the other one is going to be interactive graph analysis that I use to motivate the work. So for PageRank, we took the Twitter graph, which is used in a number of graph processing frameworks evaluations, and looked at how different frameworks processed it on up to 64 machines. And this goes from most general to least general framework. We started with Pragle, where it takes 15 seconds per iteration on a machine. If we specialize to a static graph, it takes 5.5 seconds. And if we implement the gas abstraction from the paragraph paper at OSDI last year, or in the best case, we can iterate on that graph in 1 second per iteration on 49 machines. For comparison, if we plot the paragraph results from OSDI last year, we see that our implementation of the gas abstraction is a little bit faster than the paragraph one. And this gives us some confidence that the underlying primitives are efficiently implemented. So static PageRank's pretty dull. I want to return to the application that motivated this system. And to make things concrete, we're going to process 32,000 tweets per second on a cluster of 32 machines and fire in 1 query every 100 milliseconds to measure the query latency. And this doesn't come anywhere close to saturating the query throughput, but it does let us see the latency at a fine granularity. So there are more results in the paper, but I think this captures it best. The time series shows the latency of queries as time goes on, and latency on a log scale. Only one of these 200 queries I'm showing you took over 100 milliseconds. The 99th percentile is 70 milliseconds, and the median is 5 milliseconds. The latency spikes are due to some interference from the batch workload, and we have ideas for how to reduce these by making the batch more cooperative, but that's going to remain in future work. And that brings me to the end of the talk. So hopefully, I've managed to convince you that by reducing the latency of distributed computation, Naiad can achieve the performance of specialized frameworks while also providing the flexibility of a generic framework. So it's our hope that by exposing this low-level timely data flow API, we can spur parallel innovation, allowing people to make new programming models on top of the API, while new feats of systems engineering go on underneath to improve the performance for all users. And it's for that reason that we decided to release Naiad under the Apache open source license. You can get the code from our GitHub repository. It runs on .NET and Mono, on Windows, Linux, and Mac OS. There's more information on the project website and the blog, but I'd like to thank you all for listening and take any questions.
Imranul Haq, VMware. So you mentioned that you have techniques that actually eliminate the micro-stragglers, but do you do anything about the stragglers? So for example, one machine might have more load than the other machine.
Sure. Right, so need to add a caveat. We did not eliminate the microstragglers. We still have tails in our latency plots, so that's still ongoing work to get rid of them more completely. In terms of dealing with those kinds of stragglers, dealing with those is a much longer term task. So we haven't put anything in the basic model that deals with stragglers. If you were wanting to deal with this, there are various algorithms, for example, from the database community that deal with skew and joins and other kind of aggregation operators that we can implement by adding a feedback loop to the data flow that combines some statistics about the aggregations to decide which keys are hot and then repartition the data in subsequent rounds. So I would say that's future work, but the model is designed to be as general as possible so that I can say, yeah, we totally implement it on top.
Thank you.
Thanks.
A message from cyberspace. Naiad stops data processing while checkpointing. This suggests it is inefficient to run queries that require large state due to the runtime overhead that checkpointing will incur. How does Naiad handle queries with large state?
So as I said during the talk, the fault tolerance is an area of ongoing work, so I'm not going to pretend that this is absolutely the right answer. However, the way we dealt with it in the paper, let's see if I can call up this backup slide, was to allow two different ways of recording the state. You can either take a checkpoint during the synchronous checkpointing phase, which requires you to do work that's linear in the size of the state, or you can log as the state is updated. Taking an approach a bit like we saw in the Tango paper yesterday, where we write a log of all the operations that update the state. And this requires us to reduce the throughput a little bit. And in this particular workload, which is a k-exposure calculation, it roughly halves the throughput. But it means that there are fewer long pauses. Of course, the other side of this is that if you have a log, this is going to take longer to restore from than a complete checkpoint, because you have to replay the log and potentially do some computation. And that's why I think there's no one true story for how to do fault tolerance in a system like this. Some operators will benefit from checkpointing, some from logging, some from switching between the two at runtime based on the rate of updates to them. And what we really need is a system that can dynamically choose between these and exploit the idle time in the system to make this more efficient.